Okay, so what we have is a person who jumps from a roof of a house. So let me put the drawing here. We have the roof of a house and the person is going to jump. The roof of this house, in my case, is 3.9 meters. Okay, so this is 3.9 meters. All right, jumps and then eventually will reach the floor. Okay, so let me draw this person with very long legs. And this is the moment that she touched the floor. Okay, first question of this problem, I'll call this step 1. And the question is, what is the velocity that this person gets right before touching the ground? Okay, and this is going back to chapter 2. How are we going to solve this problem? We don't have information about time, so to find the velocity here, I'm going to use that equation, v squared equals to v naught squared plus 2g delta y. Okay, the initial velocity of this person is 0. It's like the person is dropped instead of jumping up. Okay, and what else do we know? Well, let's choose a reference frame. I'm going to choose this frame where positive is down. Okay, so with that I can find this velocity. Now v is squared is going to be 2, g is positive because g is pointing down, so 2 9.8 multiplied by 3.9. We do the square root of that and we get that this velocity has magnitude 8.7 meters per second and it's positive, meaning it's pointing down. All right. Now the person doesn't stop immediately like that. She or he keeps going down and bend his knees. Okay, so he will only finally stop after he went down, his torso went down a little bit more, so he bent his knees and then he finally stopped. Okay. Now this displacement, he moves a little bit more until he stops, and this distance here is 0.7 meters, 0.70 meters. Okay, then at this point he really stops. Okay, now the next question is find the average force exerted on his torso. So we'll be focusing on this part of his body, in the torso, by his legs during the acceleration, during this deceleration. Okay, so let's go back. Step 1, he jumps, hits the floor. Step 2, which is this next part, the torso keeps going down, he's bent his knees and eventually stops. So then the final velocity is 0. So for step 2, which is this part here, the initial velocity is the one that he had when he just touched the ground here. Okay? So this initial velocity is that 9.7 meters per second pointing down. Okay? And he's going to stop. He's going to stop because his legs will hold him and exert a force against gravity, against his torso, and stop him. Okay, so let's draw all the forces on this person. Okay, so he has this force, which I'll call the force on his torso, okay, caused by the legs. He has still gravity, mg, and the mass of this body is given to us. And the question is now, what is this average force on the torso? Okay, so this is the question of the problem. Okay, let's use Newton's law to solve it. I'll keep the same reference frame. So using that reference frame, the force on the torso is negative. The weight is positive, plus mg. And this is equal to ma. A is negative because we are decelerating. And this acceleration is up, is against gravity. So I'm going to put here minus ma. Okay. Well, now how am I going to solve this? What we have is that the force on the torso is going to be equal to mg, right, plus ma. Very careful, the problem in the manual is solved incorrectly. Okay, they say that the force on the torso is just ma. That is wrong. The manual solution is wrong. Okay, this is the correct way to solve the problem. Now, to be able to give a final number, I need to know what is this acceleration, right? And how I'm going to solve that? Again, I can use the same equation from chapter 2, v squared equals to v naught squared plus 2a delta y. The final velocity is going to be 0. I'm going to stop. The initial one is that 9.7 squared. Careful with the a, since the a is pointing up. This is going to be minus 2a, and delta y is that 0.7. Okay, 0.70. So from here I get the acceleration. I put it there and get the force, the average force exerted on his torso.